Looking at this time lapse of an exposed bridge pier, you might see a single massive block of poured concrete. But to the engineers responsible for its design and maintenance, this single structural column is represented in 4 different ways across its lifespan, depending entirely on who is interpreting the document. To a municipal planner, it is a simple 2D footprint dictating urban density. To a steel fixer on site, it's a dense, multi-layered rebar cage handling dynamic vehicle loads. Years later, to a facility manager, it is an isolated physical asset. And finally, to a demolition crew, it is a precisely sequenced target for deconstruction. This shifting utility means there is no single static blueprint that carries a project from conception to completion. In modern civil engineering, a drawing is a specialized data matrix. It is calibrated to govern a specific, isolated phase of a structure's physical existence. To understand how infrastructure is actually built, we have to trace that documentation timeline, starting from fundamental coordinate geometry, moving through legal sanction, execution, and ending at safety construction. Translating abstract theoretical design into these phase-specific formats is the mechanism an engineering team uses to prevent administrative failure, physical collapse, or operational hazards. The drafting environment an engineer selects is dependent on the physical objective. Building design focuses on enclosing space for human occupancy, while heavy civil infrastructure focuses on manipulating raw terrain over massive distances. This starts with coordinate geometry. Vertical building elements are plotted on a localized XY grid. Moving to the vertical plane, the building uses a relative benchmark. The finished floor level is set at an arbitrary baseline of +100, operating independently from global geography. But applying that localized grid to a 50-mile highway or a sprawling water reservoir results in immediate coordinate errors. For this top-down road alignment, linear progression is measured in chainage. Tick marks denote precise distance intervals along the centerline. Because infrastructure spans uneven Earth, it ties into global positioning. The bottom half maps elevation changes relative to mean sea level, matching the flat alignment. For massive load distribution, like sinking deep foundations for bridge piers, geotechnical data from borehole logs is embedded directly into these elevation profiles. The fundamental geometry chosen for the drafting environment dictates the structural scope and physical purpose of the engineering project. Before any ground is broken on a vertical building site, the initial set of drawings serves no instructional purpose for the laborers. These are submission or sanction plans. Their function is to prove to municipal authorities that the proposed structure obeys local zoning regulations and safety codes. The site plan maps out legal dimensions, specifically setbacks, the mandatory empty perimeter space between the outer walls and the property boundary. The most heavily scrutinized element on this composite sheet is the area statement. This calculation table establishes the floor area ratio, or floor space index. It mathematically proves that the total proposed construction volume stays within the legal maximum for that specific plot of land. These are binding legal documents, where the recorded dimensions dictate property taxes and occupancy rights. Because of the legal liability involved, the title block mandates official municipal stamps and the signature of the licensed structural engineer taking responsibility for the design's safety. A sanction plan is a legal contract translated into geometric shapes, designed to protect the municipality from unsafe or unlawful urban density. Once approved, the project moves to execution. As seen in this close-up, the site relies on a complex network of steel and concrete. To build this framework, the execution team requires Good for Construction, or GFC, drawings. These are technical micro-instructions meant for foremen, steel fixers, and concreting crews. The structural engineering set translates theoretical safety mandates, like the Indian Standard 456 for concrete design, into executable field instructions. They dictate precise execution metrics, concrete mix grades, clear cover requirements, development lengths, and lap splice locations. While structural drawings build the skeleton, architectural working drawings dictate the enclosure. They specify exact masonry block thicknesses, lintel heights, and floor tile starting patterns to minimize material wastage. Generating these instructions also serves as a line of defense against human error. Draftsmen use this phase for proactive clash detection. This 3D diagram highlights a hazard, a mechanical layout intersecting the load-bearing framework. Routing a pipe through a concrete beam compromises integrity. To resolve this, Draftsman issues sleeve drawings, mapping where hollow PVC pipes go inside the formwork before pouring concrete. Leaving a pre-planned tunnel for the utilities prevents the dangerous practice of core-cutting structural concrete after it has cured. Drafting GFCs is the process of virtually resolving physical physics problems before they trigger delays on site. When the building is completed, the documentation matrix shifts again. Drawings evolve from instructional manuals into diagnostic tools. Facility managers rely on as-built drawings. During construction, field modifications are always made to solve on-site realities, meaning the original GFC drawings cannot be used for post-construction maintenance. For hidden utilities, MEP-concealed layouts, specifically electrical single-line diagrams, allow electricians to trace and isolate power zones without breaking through finished walls. Eventually, the structure reaches the end of its life. Tearing it down is essentially reverse construction, requiring engineering rigor to ensure a safe sequence. Architectural demolition plans use industry color coding. Elements slated for removal are marked with dashed red lines, while structural components that must be retained are drawn with solid, heavy ink. Without visual guidance, structures risk progressive collapse. The structure is dismantled strictly from top to bottom, slabs, then beams, then columns. When removing load-bearing elements, plans dictate where temporary steel shoring is installed to safely transfer weight down to the foundation. Before any machinery arrives, utility disconnection layouts map out the isolation points for high-voltage lines and pressurized water mains, ensuring the site is safe. Precise engineering documentation forms the barrier between a controlled operation and a public hazard. The documentation matrix starts as a legal boundary for sanction, evolves into an execution manual for laborers, and ultimately serves as a diagnostic map for deconstruction. Synchronizing these disparate, phase-specific layers of data across separate teams and years of construction creates significant technical friction. Today, that friction is addressed through the modern standard of building information modeling. This 3D model represents the digital twin. A digital twin synthesizes the entire life cycle. It embeds the legal zoning data, the structural execution metrics, and post-occupancy maintenance schedules into a single, unified digital asset. Selecting a single air conditioning unit within this digital model instantly reveals its installation date, warranty limits, and exact spatial coordinates for the maintenance team. The physical acts of calculating gravity loads or pouring concrete are guided entirely by this underlying data management. Engineering rigor lies in the flawless communication of complex, phase-specific spatial data across the entire physical lifespan of a structure.